Okay, last law, law 3. The ratio of a planet's orbit period squared to its orbital radius cubed is a constant. All objects orbiting the same focus, so same center point. So when we think about our solar system, our center point would be like the sun. So all of the planets that are orbiting our sun will all have the same Kepler's constant. But other planets orbiting different suns or other things orbiting different masses will have a different Kepler's constant. Sorry, we'll have the same constant. So keep in mind that this really applies to the same focus point. So basically all of these words mean this mathematically. So K, which is Kepler's constant, is equal to the period squared, so period squared, to its orbital radius cubed, so over r cubed. So what I really want you to understand is that this constant, so its time and its radius are kept constant around the same focus point. So just like I said, you can only apply the same Kepler's constant to the same objects that are all orbiting the same other object. So the square of the period of revolution of a planet about the sun is directly proportional to the cube of its mean average. So this mean average distance, remember that's orbital radius. So now this proportional, this is mathematically, so r cubed is proportional to t squared. So then I'll just show you that same video, just starting where he talks about law 3. Oh, did I exit it? Nope. At 8 minutes.
And it is a comparison of just those two bodies. In this case, Kepler's third law looks at something a little bit different. If we have a situation where we have multiple objects that are going around the same central object, like this picture I've identified here, we can make a comparison between the orbiting objects. So I could, for example, I could compare the green or the purple to each other. I could compare the green and the red to each other. Or I could compare that purple to that red. I can make a comparison of those two objects. But in this case, notice I am not going back and looking at that central massive object anymore. Kepler's third law is a comparison between multiple orbiting objects. Let's take a look at the equation. The capital T stands for the orbital.
Okay, so we won't go into too much detail about the equation because you don't have to do it. So Kepler was able to describe how planets, not plants, change that to planets. Change it to planets. Not plants. Who's not a botanist. Move from observations. But Newton was able to describe why planets move the way they do. And that's what we're going to be studying on Friday. So how this all applies to Newton again. It always comes back to Newton. And another thing to note, that when you're actually using Kepler's law, using kilometers or meters is really difficult because you're dealing with space and things spread out very far apart. So they use something called an astronomical unit. So again, I just want you to be aware of this. You don't have to use it, but know what an AU is. So an AU is the mean orbital distance from our sun to Earth. Okay, which is 1.5 times 10 to the 8 kilometers. AU is therefore a more manageable unit to use for planetary questions. If we use Earth years, we can modify our formula. But I'm not going to show you how to modify it because you don't need Okay, and then one last video to just kind of recap everything. I hope you like this one.
Fascinating.
See, look at how
Please
it's
spark to me,
slow
sir.
and fast.
Don't say it's fascinating. No. But it is interesting.
Ha ha ha, Star Trek. Okay. Who likes Star Trek?